trying to put the electron, okay, into the element. So we put the electron in terms of, okay, the lower energy level will go, and then you go to the higher energy level. Now, from this element, we are removing electron. Okay, we are removing the electron. So what is the definition of ionization energy? Okay, ionization energy, okay, you have first ionization energy, second ionization energy, third ionization energy, and the list can continue until all the electrons in that element is completely removed. Yeah. So let's actually look into first ionization energy. What is first ionization energy? But before we go into first ionization energy, please remember, yeah, if you want to remove the electron, okay, if you want to remove the electron, you must remove the electron from the part where there is going to be less attraction of the nucleus towards the electron. So you don't remove the electron from the inner shell, okay, the one that is going to be closer to the nucleus, because the attraction is going to be the strongest over there. So what we do, we try to remove from the valence electrons, or the outermost shell, okay, and we try to remove from there. Yeah. So when you remove the electron, so you see the first ionization energy, what is the definition? Is the energy required to remove one electron, okay, from each atom in 1 mole of atoms of the element, and it must be in gaseous state to form 1 mole of gaseous 1 plus ion. Now, it may be too complicated, maybe too many terms, but it is simply represented. Let's say if you have sodium, okay, so you are going to remove 1 electron from each atom in 1 mole of atom of the element in gaseous state. Now, sodium is a metal. Okay, under standard conditions, sodium is going to be in solid form, but you do not remove the electron in form of solid. Okay, you remove the electron in terms of gas. So the element must be in gaseous form. That is very, very important. And when you remove the electron, okay, what happens when you remove the electron? You are going to get Na plus. If you remove something, 1 electron from gases, it suddenly won't change from gas to liquid or gas to solid. It will still remain as gas, and you will get this 1 electron. So this one, we are talking about 1 mole. Yeah, so it means I am removing 1 electron from sodium in gaseous state. Okay, so this is going to be forming 1 mole of gases 1 plus ion. So this is the equation. Okay, this is first ionization energy. Now, if I want to write it further, and then I want to say second ionization energy. Second ionization energy, it means you have already removed 1 electron from sodium, and you are going to remove, okay, from the sodium Na plus, okay, you are going to remove 1 more. Okay, which is, okay, we know it's going to be sodium is 281. Okay, when you remove 1, so normally it's common to see Na plus, but maybe it's very uncommon, okay, when I write it down as Na2 plus. But do remember, Na2 plus can happen, okay, but it requires a lot of energy. Yeah, a lot of ionization energy is required. Okay, why? Because once you remove the 1 electron, okay, the another 1 more electron is going to be removed from the inner shell, which is going to be closer to the nucleus. Okay, and they are already stable. Yeah, all the 8 electrons are there, and you are going to actually try to remove the electron. Of course, you require a lot of energy to remove that. Okay, so you are going to have Na plus. So how do I write it down? From Na plus, I will get Na2 plus gas. 1 electron you already removed. So now you are removing another 1 more electron. So this is the equation, okay, for the second ionization energy. So if I want to write down for the third ionization energy, it's quite simple. Na2 plus, okay, from Na2 plus, and it must be in gases, you are going to form Na3 plus gas plus electron. So please take note how to write the equations. Yeah. So I will just move on. So you can see here, okay, you can remove the electrons from an atom until only nucleus is left. So if you have sodium 11 electrons, I can actually make sodium into Na plus. I remove one electron until, okay, I can have Na2 plus. I can go on, okay, until I remove all the 11 electrons. So you can have Na11 plus, okay. This is possible, okay. Theoretically, it's possible, yeah. If you have enough energy, you can remove all the way to give you Na11 plus, okay. And these ionization energies are called successive ionization energies. What are the successive ionization energy? First ionization energy, second ionization energy, third ionization energy, fourth ionization energy, and so on. It is called successive ionization energies. Yeah. Now, if you look at this discussion over here, okay, so there are equations, okay, write down the equations that describe, okay, first ionization energy of calcium. So how do I write down ionization energy of calcium? So you can see calcium must be in gaseous form, okay, first ionization energy to give you Ca plus in gases and then electron, okay. But let's say we want to write down for fifth ionization energy of sulfur. So how do I write down for the fifth? Okay, do remember, if fifth ionization energy of sulfur, it means I am removing the fifth electron. Okay, I am removing the fifth electron. It means that I have already 4 electrons have been removed in the past. Okay, I want you to remember this. So fifth ionization energy is sulfur must be 4 plus. You start from there. It means fifth means I'm removing the fifth electron. 4 electron has been removed earlier. So you have S4 plus. It must be in gaseous form. You remove so that you remove one more, so you have S5 plus. Okay, and then you have the electron. So you can see this is how to do. Okay, is that clear, Patricia?
Yes, sir.
Okay, you can actually look at it later. Yeah, the rest of it. Now here, okay, let's look at B. The second ionization energy of nitrogen, okay, is 2860. The third ionization energy is 4590. Okay, explain why the third ionization energy is higher. Okay, before we try this question, yeah, I just want you to think about this. Yeah, if I have, okay, let's say for example, this is sodium. Okay, this is sodium. And then sodium, okay, has 11 proton, okay, and it has 11 electrons, okay. And then when I remove one electron, so what happened? Okay, sodium now, okay, I am going to have, okay, the same 11 proton, but now I am going to have only 10 electrons. So I have sodium Na plus. This is Na. Okay. Now, what is the difference between these two? I already told you last time. Okay, the proton, okay, will contribute to the nuclear charge, the positive charge. Yeah. So the proton will hold the electron as though like they have one arm. They are going to hold the electron closer. Okay. They will not let the electron go. So 11 proton, 11 electron. Now, when you took away one electron, okay, Now, what happens? Okay, you have 11 proton and less electron, 10 electron. So what happens? Okay, if someone steal money away from you, of course, okay, you will not let it happen again. You will hold to that money as tight as possible. Okay, similar to Na plus, okay, because they have 11 proton, more proton than the electron, they will really hold the electrons. Okay, and it's going to be very, very difficult to remove. Yeah, so let's say to remove one electron, maybe you have about 100 joule of energy. Okay, you use 100 joule of energy. But when you remove the second electron, maybe you require higher energy. Yeah, why? Because okay, the proton is holding the electron. Okay, tight. Okay, but okay, there are certain conditions. Okay, do look at 281. Okay, and then when you remove one electron, you get 28. Now, the one electron has been removed from the principal quantum shell. Okay, that is going to be further away from the nucleus. But the second electron, if you want to remove, okay, if I want to form Na2 plus, I am going to remove it from the inner shell. Or to use the correct term, I am going to use to remove the electron from the principal quantum shell that is closer to the nucleus. Okay. Now, what happens? Okay, because of that, okay, we know that the charge, okay, the nuclear charge is more, they are trying to hold the electron. But now, not only because of the charge is strong, okay, the shell itself is closer to the nucleus. They are going to be way, way stronger. Okay, so if you have increased, okay, from 100 okay, to 300, yeah, for example, but if you go to the inner shell, maybe the jump is more than what you expect. Okay, so maybe let's say when you remove, okay, your first ionization energy is going to be 100, okay, but you expect the second ionization energy is supposed to be 300, but suddenly you will notice it's not even 300. Suddenly you notice it might be 1000 joule. Okay, it suddenly the jump is really, really big. Okay, if the jump is really, really big, okay, it is because okay, the electrons are removed from the inner shell. Okay, because the electrons are removed from the inner shell. So please take note. Yeah, please take note. So there are few factors that you need to notice about that. Yeah. So here, okay, let me answer this question first. Okay, second ionization energy of nitrogen. If you look at nitrogen 7, yeah, so 1s2, 2s2, 2p, 2p. Okay, I just write down. So 4, this is 2p3. Okay. So do remember this is going to be from the same principal quantum shell. Okay. 2. Yeah. So when I remove, they say remove second ionization energy. You remove one still from the 2p. You remove the second is still from 2p. And you remove the third, it's still from the 2p. You are not moving from the outermost shell into the inner shell. Yeah. So they say just this one is like normal. Okay, remember that 100 to become 300. Okay, why? Because similar the one that I mentioned, if someone steal the money away from you, if they try to steal again, you will hold it tightly. Yeah, only that, nothing to do with the inner shell and so on. So in this case, the third electron is still being moved from the same subshell. Yeah, so you just need to explain, okay, there will be more positive charge and they are going to hold the electrons closer, difficult to remove. So you can see here, the charge of the ion, the positive ion, is going to be greater when the third electron is removed. So therefore, it's difficult because there is a greater attractive force between the outer electrons and the nucleus. Okay, it means just to tell that okay, your nuclear charge is more, okay, so they can hold the electrons closer, okay, so more attractive forces, yeah. But as I mentioned to you, okay, previously, there are few factors that will affect the ionization energy. One is going to be the size of the nuclear charge. It means that if you have more nuclear charge, it means more proton, okay, you will have more positive charges that are going to be able to attract the electron closer to itself. Yeah, so they will not allow the electrons to be removed. So one, the size of the nuclear charge. Second is the distance of the outer electrons from the nucleus. So if you want to remove the electrons, we need to consider about the distance. The further that they are, okay, the further that they are going to be easily be removed. Your ionization energy is going to be lesser. Yeah, the nearer to the nucleus is going to be more difficult to be removed. Yeah. Now, another one is going to be shielding effect of inner electrons. This one I have already taught you, okay? Shielding effect is going to be if, let's say, the electrons, the nucleus, they want to actually hold the electrons, okay? All the electrons, okay, that actually comes within the inner shell. So let's say if I want to remove this electron and you have two electrons over here, the two electrons in the inner shell, they are going to provide what we call a shielding effect. Okay, this shielding effect will cancel or disrupt the attraction of the nucleus towards the this particular electron. So this will actually disturb. Okay, this will disturb and making the attractions to be slightly weaker. Yeah. Now, just have a look at this diagram. Then after that, the rest of it, we will continue next lesson. Yeah. Now, if you look at this diagram, yeah, this is going to be the diagram, graph to show the successive 11 ionization energy. It means you remove one electron, okay, from the sodium all the way until you remove 11 electrons away from the sodium. Okay, so Mayumi, why I cannot remove 12 electrons from sodium, Mayumi? Nah, Mayumi is MIA. Mayumi, I can still see your head. Can you answer? Why you cannot remove 12 electrons from sodium?
Because it only has 11.
Yes, because maximum we only have 11 electrons. Yeah, sodium is 11. Yeah. So anyways, okay, what is the general pattern that you can see, Rakesha, when it comes to ionization energy and the electrons being removed? Increasing, decreasing, remains the same?
It increases as the number of electrons increases.
Okay, can you tell us the general reason why it increases? Rakesha?
Because it's harder. If there are more electrons, it is harder to like break the bonds.
No? All the terms that you use is wrong. Yeah. Please remember, as you remove the electron, okay, the number of electrons in the sodium, yeah, or the sodium ions, okay, the number of electrons are decreasing. Okay, the number of electrons are decreasing. The number of proton remains the same. Okay, so you will have the more proton compared to electron. So if you have more proton compared to the electron, it means your nuclear charge, okay, nuclear charge is more, okay, it's getting more, or you can say the nuclear charge is more. So the attractive forces from the nucleus to hold the remaining electrons are generally going to increase. Is that clear, Rakesha? Okay, it means just have a look at this example, yeah. So sodium have 11 proton, okay, you remove one, you have 10 electrons, okay. So positive 11 holding -10. Okay, you can look at it in that way. But at here, it's going to be 11 proton. How many electron? Okay, you have 0 electron. So here you have 11 proton, you only have 1 electron. Just imagine 11 positive charges holding only 1 negative charge. Okay, it's so going to be difficult, okay, to remove it. That's why, okay, you have a very high, okay, ionization energy. Okay, so that's going to be the explanation. Now let's look at, okay, something unusual. Okay, so let's actually ask someone over here. So Vanessa, did you notice any unusual patterns? Rather than wasting time, yeah. So Alden, can you notice any unusual patterns?
No.
No unusual patterns. Can you see that it's a big jump here and a big jump over here? Okay, so we need to actually find out, okay, why there is a big jump over there. Okay, so you need to actually learn how to explain why there is a big jump. Yeah, so you can see here, okay, to remove the second electron, okay, your second ionization energy compared to your first ionization energy, there is a big jump. Okay, and to remove the 10th electron, okay, if you compare with the 9, yeah, ionization energy, it's going to be a big jump. And I mentioned about big jumps can only happen when you go suddenly into the inner shell. Okay, suddenly into inner shell. So if you look at it, yeah, if you have two, if I just write down, okay, in terms of SPD, 1s2, 2s2, 2p6, 3s1. Okay, this is going to be the electronic configuration of sodium. So when you remove the 1 electron, okay, the 1 electron from here, you are removing the 1 electron from here. Okay, so this one represents this. Okay, but the second ionization energy is being removed from which subshell, Alden?
From the third.
Third, are you sure? From here, right?
Yeah, from the 2p6.
Yeah, the subshell. Oh, you count from here 1, 2, 3. Okay, you just always tell the subshell is 2p. Yeah, so you can say whenever I say which subshell, 2p. Yeah, that's should be the your answer. So in this case, you are removing it from 2p subshell. Okay, and 2p subshell is going to be the principal quantum shell that is going to be different than 3. Yeah, so even you see S and P, they are going to be the same principal quantum shell. Yeah, so they are still, the energy level is still okay, but from 3 to become 2, yeah, you are moving from a different principal quantum shell. So therefore, they are closer to the nucleus. Okay, to remove them, the electron, the first electron over there is going to be very, very difficult. Why? Because it is closer to the nucleus. Okay, or it is located in the subshell, 2p subshell, which is closer to the nucleus, which is going to be attracted greatly, okay, with the by the nucleus. Yeah, so it's going to be very hard to remove. But after that, if you want to continue to remove the 8 electrons from here, okay, the 8 electrons over there, it's going to be easy. Why? Okay, because they are from the same principal quantum shell. Okay, so you remove the 1, 2, 3, 4, 5, 6, 7, 8. Okay, so no problem, but they will increase. Okay, why? I already told you the positive charges are more, okay, the electrons are less, so they are generally going to increase over there. But there will be suddenly a great jump from 8 to 9. Why? You are removing from which subshell when it comes to this over here. So Vanessa, which subshell are we going to actually remove when it comes to the 10th ionization energy? Rico. Okay, Vanessa, continue, yeah?
The one S.
Yes, okay. You are removing from the subshell, which is going to be 1s subshell, yeah, which is very, very close, okay, to the nucleus. So you are going to have a big jump over there. And after that, still similar, okay, because it's from the same subshell, yeah. So they will follow like that, yeah. So I hope you can understand, okay, about this, okay. The takeaway is going to be you can remove the electrons, okay, from, okay, you remove the electrons, generally the ionization energy will increase. But the increase will be sudden, or suddenly it will become too great, okay, the moment when it comes, okay, where the electrons are being removed from the inner shell. Yeah, so that is very, very important. So now, okay, I want you guys, okay, you have your iPad, okay, okay, you have your paper and so on, okay. I want you guys to sketch, okay, to sketch the graph, similar graph like this, okay, similar graph like this for, okay, hold on, let me think. Sketch similar graph like this for Scandium. Okay, can you guys do it now? Scandium. So while I'm doing also, I will ask some questions, yeah? So Kathleen, I will start from here, number 1, all the way end with number 1. I need to wait so long for the answer. Yeah, Rakesha, okay, all the way to number. Sodium, you have 11 electrons. So I remove 1 electron, all the way to remove everything is 11. So if I have scandium, 21 proton and 21 electron. So I want you to draw for all. Okay, it means that number 1 all the way to number what? Rakesha.
21.
Yes. Okay. So we are going to do this. Okay. So try to sketch. Aaron, can you write down, tell me what is the electronic configuration of scandium? Okay, we can do it together now. Scandium, 1s. Yeah, Aaron. Unmute first.
1s,
One.
2s, 2p,
2s2 p6. So that's already 10.
3s,
2, 3p6. And then start with 4s2. Okay, that's already another 10. 3d how many?
1.
Yeah. Okay. So when I remove the one electron, remember last time I told you when you fill up the electron, you remove from 4s. You put from 4s first. And removal also must come from 4s first. Yeah, please remember. Yeah, it means that the 4s and 3d, okay, the energy level is almost the same. Yeah, it's almost the same. So you remove the first two electrons. So let's say I sketch now, yeah. The first two electron, okay, when I remove from 4s, okay, it's still the same. Now, when you go to 3D, okay, please remember, okay, it is going to be almost the same, okay, because even though it's different principal quantum shell, okay, because the energy level, okay, is going to be almost the same as 4s. Okay, the increase is not a big increase, maybe something like this only. Okay, number 3. Okay, then you remove from 3p, 3s. So there are 8 electrons. Okay, so you all these 8 electrons, they are going to increase gradually. Okay, because they are going to be from the same energy level. Okay, they are going to be the same principal quantum shell. Okay, so you can actually put down, okay, 8 electrons. So from 1, 2, 3, 4, 5, 6, 7, 8 up to 11. So maybe I just put up to here. Okay, so I can sketch all the way. They increase like this. Okay. And then this one like this, this one like this. Okay, so it means this one done, this one done. Now, the next is I am going to remove, okay, the 12, okay, electrons. The 12 electron or the 12 ionization energy, okay, must be coming from subshell 2p. Okay, must be coming from subshell 2p. And 2p is going to be a different principal quantum shell. Okay, so where should I put for 12? Yeah, so Alden. So should I just increase little bit like this, or should I go all the way to here? Position A or position B? Which one do you think? Alden.
B.
Yeah, very good. Okay, because if it is A, then it's similar to this. Okay, which is, okay, we don't want similar to this because this one is almost the same energy level. So this one we are talking about a different energy level. Yeah, so we are going to have all the way to B. Okay, not A. So after that, the 8 electrons, yeah. Okay, it means 1, 2, 3, 4, 5, 6, 7, 8, up to this 19. They supposed to increase, okay, gradually. So maybe I stop here like this. Okay, and then you have this 1s. Okay, so you are going to have a different, okay, you are going to have another subshell. Okay, another subshell. So there should be another sudden increase, yeah. Okay, so therefore Okay, maybe what I do. Like this. Okay, so maybe I'll just make it longer. Ionization energy. So now, okay, they are going to go way up. And then, okay, this is 20. Then the last one should be just, okay, similar. Because why? Because it's going to be the same energy level, the same subshell. Okay. Is that clear, guys? Okay, so you should be able to understand a lot of things over here. Okay, but if I want to summarize, okay, what affects successive ionization energy? Okay, successive ionization energy. They are factors, okay, that will affect the successive ionization energy. One is going to be the nuclear charge. Okay, the nuclear charge. Okay, overall, yeah. So when you have more nuclear charge compared to the electrons, generally the attraction will be greater. So generally, you can see increase in ionization energies. Yeah. Then number two, okay, it depends on the distance. Okay, distance, okay, between the nucleus and depends on the nucleus and also the electrons that is being removed. And number three, it depends on shielding effect. Okay, ionization is also affected by the shielding effect. Now, I will continue this slightly further. Okay, I hope you still remember. Okay, I told you to when I ask in future about periodic table. Okay, there are few things that should be coming in your mind. Yeah. So when I say periodic table, okay, your periodic table automatically in your mind. Okay, this rectangle should be automatically being built in your mind. Okay, means there's a rectangle. Okay, and there should be one arrow going here. Okay, this is the thinking process that I want you to develop. Yeah, so there should be a rectangle appearing in your brain, and then there is one arrow there, and there should be one arrow going down. Okay. And I want you to remember, okay, there will be, okay, in this case, big circle, okay, and then, okay, the big circle starts to become smaller and start to become smaller and start to become smaller. Okay, I taught you when I teach you about atomic radius. Okay, we are going to use this again. Yeah. So as you go across the periodic table, okay, atomic radius decreases. Why? Nuclear charge increases. Okay, when the nuclear charge is increasing, shielding effect remains constant. Okay, because the same number of shell. Okay, so it will actually make more attraction towards the nucleus, towards the electrons, and okay, it will become pull the electrons closer to itself, making the atomic radius to become smaller and smaller. Yep. And then going down the group, the atomic radius is going to increase, getting bigger and bigger. Reason, even though nuclear charge is increasing, okay, and I told you to memorize this, even though the nuclear charge, okay, is increasing, okay, but your increase in distance, okay, because of the increase in number of shells, okay, and the increase in shielding effect outweighs outweigh the increase in nuclear charge. Please remember this, yeah. The increase in distance and increase in shielding effect outweigh the increase in the nuclear charge, okay, making the atomic radius to become bigger and bigger. Yeah. Now, how is it going to be affecting ionization energy? Now, ionization energy, okay, it is related to this also. Yeah. What we can say is, okay, the nucleus, let's say this is the nucleus. The nucleus is actually getting stronger and stronger, okay, from the left to the right. It means it's getting more powerful. Okay, it's getting more powerful. It is holding the electrons closer to itself. If I want to remove one electron from here, okay, it is going to be easy to remove one electron on the left compared to removing one electron on the right. Okay, because it's closer to the nucleus. Okay, it's closer to the nucleus. It's going to be difficult because the nucleus is holding the electrons very closely.
Sir,
Yeah.
I think we're supposed to have chapel now.
Hey, I thought it's oh, I saw wrongly. Sorry, guys. Yeah, sorry. I thought it's actually Tuesday. Okay. I will end the lesson. Yeah, sorry. Just I'll inform Mr. Yustian also. Okay. See you guys. Bye.